Dear students, Assalamu alaikum. In this tutorial, I'm going to show you how we can build a circuit that outputs 2's complement of a 3-bit number using encoder and decoder. So this is our experiment, and we will be needing two types of ICs for this experiment. The first IC is numbered as 74LS138, and it is basically a decoder, and the second IC is 74LS148, which is known as an encoder. So basically we'll be using a decoder and an encoder, and we'll be building a circuit that outputs the 2's complement representation for a 3-bit number. Okay, so let's continue. So this is basically the truth table for our experiment. So I'm just gonna move into a slide right now, and I want to show you that slide because we have some very important information in this slide. Alright, so our experiment is this one. I have already mentioned the name, so let's move on. So at first I'm going to be talking about 2's complement. Okay, so maybe we already know what 2's complement is, but I'm just gonna go through a short theory so that all of us can understand what we are actually doing. So let me move into animation. Okay, so this is basically how we can do the 2's complement for a 3-bit number. So the binary of a number, let's say 0, is basically 3 zeros if we write it using 3 bits. Okay, so the binary of 0 in 3 bits is actually 0, 0 and 0. So if I want to do the 1's complement for that number, then it will look something like this: 1 1 1 1, because 1's complement is just inversing the numbers, inversing the digits, right? So the original digits were 0 0 and 0, and now if we want to do the 1's complement, then it will look something like this: 1 1 and 1. So this is the 1's complement representation for that number. And now if we want to do the 2's complement, then we just need to add 1 to these numbers. So 1 1 1 plus 1, and then it gives us a number of 0 0 0. So basically the 3-bit binary representation of 0 is 0 0 0, and if we do 2's complement for that number, then it produces a result which is also 0 0 and 0. Alright, so let's move into another example. So if we say the binary number of 1, and it will be 001 in case we are representing it with 3 bits. Okay, so the 1's complement representation of 1 will be 1 1 0, just inversing the digits, and to make it 2's complement we just need to add 1 to it. So 1 1 0 plus 1, and it will give us a number of 1 1 and 1. Alright, so I guess all of us now have the idea how we can actually make 2's complement for a specific number. Alright, so this is basically the truth table of our experiment. Alright, so there will be some inputs and there will be some outputs. So basically at the input part, I'll be inputting numbers from 0 to 7 using 3 bits of binary. Alright, using 3 bits of binary. So there are 3 different bits: C, B and A, and I'm assuming that C is my MSB. Alright, C is my MSB. So you can see the representations right here, that for 0 the representation is 0 0 0, and if I take a look at the output, then it also gives me the result of 0 0 0. So basically the output is the 2's complement representation for this number. Alright, so I have written it right now that this is basically the 2's complement representation for this part over here, so that we can understand it better. So if a number is 0 0 0, then the 2's complement representation will be 0 0 0 2. Okay, if a number is 1 1 1, then the 2's complement representation for that 3-bit number will be actually 1 1 and 1. Okay, so I have done all the necessary 2's complement representation for all of those main terms. All right, for all of those main terms from 0 to 7. So let's say another example, maybe the last one, 1 1 and 1. Okay, so this is my original number, this is my input, and in the output part I want to get the 2's complement, because remember our experiment name, our experiment was something like this, that we want to calculate the 2's complement representation for a 3-bit number. So our 3-bit number is this one, 1 1 and 1, and if I want to do the 2's complement for this number, then I should be getting 0 0 1 at the output. All right, so this table right here just shows the actual truth table for our experiment, where we're actually inputting 3-bit numbers, and we intend to get 2's complement representation for those 3-bit numbers. All right, so this is basically the truth table. And if you want to take a look at the main terms, you will also understand that how the main terms are actually written here. For example, in the input part, you can see that I have written all the main terms sequentially from 0 to 7, and these are the binary representation using 3 bits. And in the output part, you can see that the first binary number here, 0 0 and 0, so this actually represents the decimal 0 in case of representation, right? And for the second one, we're getting 1 1 and 1, which represents 7, and from the third one we're getting 1 1 0, which represents 6, and so on. All right, so this is basically the decimal representation, which is written as the main terms for both the inputs and outputs. All right, so this is how the truth table works. This is what our experiment is, and we want to build such a circuit by which we can actually input a 3-bit number, and we should be getting the 2's complement representation for that number. All right, so let's move into another part. So however, there is a twist, because if the IC we are using is an active low IC, all right, if the IC we are using is an active low IC, then the outputs will be reverse of the original output. Okay, so what does it mean? It means that if my original output is 0 0 0, like it is here, if my output is 0 0 0, then since we want to use an active low IC, then the output should be something like 1 1 and 1. Okay, so 0 0 0 will be shown as 1 1 1. If my output is 1 1 1, then the active low IC will produce 0 0 0 at the final stage. All right, because it is an active low IC. So for another example, if I say that the output is 1 0 0 1 0 0, then for the active low IC, the output will be shown as 0 1 1. All right, so basically what an active low IC is doing is that it is actually reversing the original output. Okay, so it is actually giving us the inverse output, basically the inverse output of the original output. Okay, so if we are getting 0 1 0, then the output will look something like 1 0 1. All right, so I guess you now have the idea of what an active low IC does. Alright, so you should be able to get more ideas about active low ICs if you search over the internet. So I'm not going into further details of that IC. Okay, we just need to understand what the perspective of active low IC in our experiment is. Okay, so let me just make it more clear. So yeah, I have already explained you that, but let me just show you in a more calculative way. Okay, so if I take a 3-bit number, let's say the binary of 0, so 0 0 0, this is a 3-bit number, so the 1's complement of that number will be 1 1 1, and we can add 1 to make it 2's complement, so the 2's complement will be 0 0 0. However, if we use an active low IC, then 0 0 0 will be shown as 1 1 1 at the final output. Okay, so that's what an active low IC does. So if I take the binary of 1, so you can see that after adding 1 to the 1's complement number, we will be getting the 2's complement representation for these 3-bit numbers 0 0 1, and the 2's complement will be 1 1 1. All right, so if I use an active low IC, then basically this output will be shown as 0 0 0 at the final output. Okay, so I hope all of you understand how an active low IC works. All right, so let's move into our next topic. Okay, so this is basically the truth table, the extended version of our original truth table. Okay, so previously I did show you. Okay, so let me just rewind a bit. Okay, so this was our original truth table, and now I just want to show you the extended version of this truth table. Okay, so you can see that the rightmost part over there, the active low output part over here, was not actually included in the original truth table. Okay, so this is the new part, and I have already explained how an active low IC work. Okay, so let's say that the original output was 000, so for active low output it will show the output as 111. If the output is 011, then since we want to see the active low output, then the output will be something like this one. Okay, 100. If you get the original output as 010, then the active low output will be 101. All right, so this is basically the truth table where we are including our active low part too. Okay, so our whole circuit, our actual circuit, will be built depending on this truth table. Okay, so we will be building our circuit, and then we'll be verifying our circuit whether it actually works or not based upon this truth table. Okay, so now I'm going to move into Proteus Simulation Software, and I will be building the circuit where I can actually convert 3-bit number to its 2's complement representation, and I will be showing the output as an active low output. Okay, so let's move into our main simulation experiment. All right, so I have already explained that I will be using 2 different ICs for my experiment at the beginning of this tutorial. So the left most IC right here, so this is a decoder, and the rightmost one is an encoder. Okay, so I'll be using 2 different ICs. The left one has an IC number of 74138, and the right one has the IC number of 74148. Okay, and this will be the connection procedure. I'll be showing this when I build this again. Okay, so this is basically the connection procedure. The output of the zeroth output of this IC will be connected to the 0th input of this IC. So the number 1 output will go to the 7th input of this IC, and the number 2 output of this IC will go into the 6th input of this IC. Okay, so this is basically the IC diagram. This is basically the circuit diagram, okay, for our circuit. So I will be building this circuit in Proteus Simulation Software. So let's move on to Proteus Simulation Software. Okay, so I'm already in the Proteus software, so I just want to take 2 different ICs. So the first one will be 74LS138. So you can see right here that this is the IC which is known as decoder. Okay, 3-line to 8-line decoder. So basically this IC will be working in a way by which will be inputting, will be giving it 3 inputs, and it will produce 8 outputs. That's why it is called a 3-line to 8-line decoders. Okay, so let me just take this one, and I also want to take 74LS148. So yeah, this one. So for showing the input, I'll be taking logic states, and for outputs, I'll be using, I can use basically 2 types of things. One is LED light, and another is logic probe. So in my previous tutorials I actually used LED lights. So let me just show you how we can also see the outputs using logic probes. Okay, so I want to take logic probes for this experiment. Okay, so this should be enough for our experiment. Okay, so let me take the ICs first. So if you can check out the diagram right here. So the diagram clearly shows that the left one is the decoder and the right one is the encoder. So at the left part, I want to take my decoder. Okay, so yeah, let me just put it right there. So this is the decoder. You can see the number 74LS138. This is actually the decoder. Okay, so there are three inputs, A, B, C. Okay, three inputs, and C is my MSB. I'll write it within a bit. So C is my MSB, and there are three inputs and there are 8 outputs. So decoder is such an IC which can actually produce more outputs than the inputs. Okay, so we're using 3 inputs and we're getting 8 outputs, and basically it works with the formula of n 2 to the power n. Okay, so if there are n number of inputs, then we'll be getting 2 to the power n number of outputs at the right side. Okay, so we're having 3 inputs right here, and 2 to the power 3 means 8, so we are getting 8 outputs at the right side. Okay, so this is basically the working principle for a decoder. So we'll be giving it n number of inputs and we should be getting 2 to the power n number of outputs. Okay, so this is basically the decoder part. So let me move into the encoder. So encoder is basically the opposite of decoders. Okay, so in case of encoder, we'll be giving it 2 to the power n number of inputs. So we're giving it 8 inputs right here from 0 to 7. You can see the pin numbers. So the pin numbers are actually on the left side, 10, 11, 12, 13, 1, 2, 3, 4. So these are just some indication, just some sequence numbers. So these 8 pins right here. Okay, so these are the input pins and we're giving it 8 inputs. So based upon the principle of 2 to the power n to n, so we should be getting 3 outputs. Okay, and these are the 3 outputs, A2, A1, A0, assuming A2 is my MSB. So these are the 3 outputs. So we're giving it 8 inputs and we're getting 3 outputs. Okay, so this is the working principle for an encoder. So in encoder, we usually give it 2 to the power n number of inputs and we get n number of outputs at the right side. Okay, so this is basically the encoder part. So now I just want to connect them together. So at the very beginning, I want to connect the inputs. So let me just take the inputs first. So I'll be connecting the inputs to my decoder first right here. Okay, so I'll be just connecting them like a regular circuit, nothing else. Okay, so my inputs are connected and you can see that there are 3 other pins too. So one is E1, then E2 and E3. Okay, so these are basically known as enable pins. Okay, these pins are required to be connected to some values so that the IC can actually work. Okay, these enable pins are actually required. The enable pins which are situated at the input side are actually required and you need to connect them somewhere to get the IC working. Okay, so let me just tell you how you can actually connect them. So you can see the E1 part here. This is basically a simple straightforward input connection. Okay, and you will be connecting it to 5 volt. Okay, to 5 volt. Basically you can connect 5 volt using this power module. Okay, so I'll be connecting this one to this power or 5 volt connection. Okay, and for the rest of the two, for the remaining two, okay, E2 and E3, you can see that there are 2 small circles at the end of these input connection. That means these should be connected at ground. Okay, this should be connected at ground, or these should be connected to something which has a value of 0. Okay, so I'm going to be connecting them into ground. So you can actually also connect them to a value of 0. Okay, like if you want to take a logic state, over here and then connect both of them to that logic state, it will also work if the logic state has a value of 0. Okay, so I just connected them to ground because it's much simpler. Okay, so that's it. So this is basically the input connection for this decoder over here. Okay, so now I want to give the middle part. I want to give the connection to this middle part over here. Okay, so you can see that the 0 will be connected to 0, the 1 will be connected to 7, and 2 will be connected to 6, and so on. Okay, so let me just connect it together, and let me tell you that the 0 you are seeing here. Okay, let me just zoom in. Okay, so the 0 you are seeing here is actually the 0 uh, which is shown here, y0. Okay, y0 is the thing that you are seeing here as 0. The 1 is actually shown here as y1. Okay, and for the right IC, the encoder, you can see 0 1 2 3 4 5 6 7, and you can also see right here 0 1 2 3 4 5 6 7. All right, so I'll be just connecting them based upon this connection over here. Okay, so let me just connect it. So 0 will be connected to 0 will be connected to 0. 0 is connected to 0. Then 1 will be connected to 7. Okay, 1 will be connected to 7. That's it. And you can see the 2, y2. Okay, 2 will be connected to 6. So let me connect to 6 right here. Okay, 2 is connected to 6, and I'll be connecting rest of the things based upon this diagram. Okay, alright, so I have completed all the connections in this middle part. So the connections between the decoder and the encoder. Okay, so just one connection left right here. So this is basically an enable pin which works for the encoder. Okay, so you can see right here that there is a small circle at the end of the connection. So this should be connected to ground or a 0. Okay, so since we already have a ground here, so I'm going to be connecting this one to that ground connection. Okay, so that's it. So the inputs of the encoder are also done. So just the outputs are left. So now I want to connect the outputs. Okay, so I have already told that for this experiment I want to use the logic probes to show you the output. Previously I have used LED lights in all my experiments, so I just want to show you that I can also do this using logic probes. Okay, so let me just connect them. So for 3 different outputs I'll be using 3 different logic probes. Alright, so let me just connect them. Okay, that's it. So you can still see that there are 2 output connections left. So one is known as GS, and the another one is another enable pin basically. Okay, so these connections are basically at the output side. So basically we don't need to connect those for our experiment. Okay, we don't need to connect those for our experiment, so I'm gonna be ignoring this. Okay, so I just need those 3 main outputs, and I have already connected them. Okay, so my connection part is already done. So now I want to show you the simulation part. Okay, alright, so let me show you the simulation, but let me show you the output first. Okay, so the output truth table right here. Okay, so this is basically my input, and these will be shown at the decoder side. Okay, and this is basically my final output, which will be shown at the encoder side. Okay, so let me just show you the simulation, you will understand better. So let me run it. All right, okay, so let me test for the very first one. Okay, so the first one shows that if the inputs are something like this, 0 0 and 0. Okay, so the inputs are 0 0 and 0, and you can see right here that the numbers written here, C, B and A, assuming C is my MSB. Okay, so let me just write the MSBs right here so that you can understand it better. Okay, so as you can see that if my inputs are 0 0 and 0, so this is my MSB, C is my MSB. Okay, so if the inputs are 0 0 and 0, then the output I should be getting is 1 1 and 1. Okay, so let me just check whether I'm getting 1 1 and 1. So you can see at the output side I'm getting 1 1 1. So my circuit is actually working, right? So what is actually happening here is that, so I'm giving the value as 0 0 0. So basically it is transformed into a 2's complement version. So for 0 0 0, the 2's complement should be 0002, because 000, then the ones complement is 111, and if we add another 1 to it, then it gives us 000. All right. However, since we are using active low IC, okay, we are using active low IC, this is an active low IC, so the output is again transformed into 1 1 and 1, and that is what we are getting at the output. So let me give you another example. So let's say we want to see the output for 001. Okay, so this is basically the representation of 1. All right, so 001. So let me move into the truth table. So for 001, if the input is 001, then the 2's complement representation should be 1 1 and 1. All right. However, since we are using active low IC, so the actual output should be 0 0 and 0. And if you can take a look at our output, you will see that we are actually getting 0 0 and 0 at the final part of our circuit. So let me just show you for a random example. So let's say I want to check this number, okay, 101. All right, 101. So basically it is representing 5. All right, 101 is 5, so I'm giving the input as 5. The binary number in 3-bit for 5 is 101, so I'm giving this as the input, and I'm getting 100 at the output. All right, so let me check the truth table. So I'm giving 101 as the input, and this is basically indicating 5. However, the 2's complement representation of 101 is 011. All right, is 011, but we are using an active low IC, so the final output should look something like this, 100, and you can check that we are actually getting 100 right here, right? So you can also check another thing. If you want, let's say if I want to give the value as 1 1 and 1. Okay, so this is actually indicating 7, so I'm giving the value of 1 1 and 1, and here you can see that I am getting the final output as 110. And if you want to take a look at the truth table, you will also see that if the input is 111, then the final output should be 110. The actual 2's complement of 111 is 001, but we're using an active low IC, that's why the final output is 110. Okay, so this is the MSB 110 is the final output. Okay, so you can also check another thing, that originally if my input is 1 1 and 1, then the 2's complement version for that one is actually 001. All right, 001, which indicates 1. So if my original input is 111, which indicates 7, so let me show you in the circuit that for 111 only the Y7 in my output is actually blue right here. All right, so this is indicating that all other outputs are not working right now, only Y7 is working, that's why it's blue. At the input side, you can see that the active connections are indicating red, okay, but at the output side you can see that the active one is indicating as blue. Okay, so Y7 is the active one right now because we gave the input as 1 1 and 1. So at the decoder part we are getting 7 as our output. Okay, but if we want to do the 2's complement for 1 1 and 1, then we'll be getting 001 as our 2's complement representation. And you can see right here at the encoder part, the input of the encoder part, you can clearly see that right there only one blue light is seen, and this is the number 1 connection right here. Okay, the number 1 connection. So this is indicating that the main term, which is 001 is written here, is actually indicating the main term of 1. Okay, so that's why this one right here is shown as blue. Okay, so you might ask that why it is showing as blue, why it is showing as blue whereas the input connection for the decoder was shown in red. Okay, so you can check them out that the input connection was decoder, they didn't have any kind of circle at the end of those input connection, but this IC right here, the decoder, so this is an active low and the encoder. This is an active low IC, and you can see that at the input, all the inputs have small circles right at the end of those connections. Okay, so this works a bit different than those inputs. Okay, so that's why the active one is shown in the active one is shown in blue here, okay, instead of red. Okay, so and finally, if we check the output, you can see that we're getting the output as 1 1 and 0. All right, 1 1 and 0, and that's the final output we should be getting based upon this truth table. So the original, even though the original 2's complement of 111 is 001, which indicates 1, so we are actually getting that we gave the input as 111, so 7 is working. And you can see that at the encoder part, the number 1 connection is working, which is indicating basically this one, so 1. However, since this is an active low IC, that's why it got changed again, and the final output we are getting is actually 110. So if it were not, if it was not an active low IC, then the final output would be just the binary number for 1, that would be 001. That would be the final output. Okay, however, we are not using the normal IC here, we are using the active low IC. That's why we're getting the inverse of that original number. So that's why we are not getting 001, we're actually getting 1 1 and 0. All right, 1 1 and 0. So hopefully you have understood it, and this is how we can actually use a decoder and an encoder to build up a circuit by which we can actually represent the 2's complementary number for a 3-bit binary number. And we did build it, and we showed the final output as the 2's complement representation. However, we showed it using an active low IC. Okay, and this is the truth table for our experiment, and we did build our circuit, and we actually verified our circuit based upon this truth table. So this is how you can do it. Hopefully all of you have understood it in a correct way, and all of you will be able to build it later. So thank you for watching. If you have any questions, please ask them in the comment, and best of luck for future lectures.